Electricity. It's this invisible force that, let's be honest, powers our entire world. But how does it actually work? I mean, how do you even begin to understand something so massive? Well, you might think you need some high-tech lab, but the secret is actually way simpler. Today, we're going to deconstruct a simple flashlight to uncover the fundamental principles of electricity.
So, before we crack open our flashlight, let's just take a second to appreciate the scale we're talking about here. Just how deeply is electricity woven into our daily lives? Well, the short answer is completely.
I mean, think about it. From the moment you wake up, pretty much everything you do runs on electricity. It's how we watch movies, how we talk to each other on our phones, how we light up our homes and cook our food. It's even how we get around. It really is the silent, constant hum behind all of modern life.
And here is the really cool part. To understand the rules that govern that entire global system, all you need to do is look inside this humble little flashlight. It's like a perfect miniature model of how all electricity works.
Okay, so let's pop it open. What are the key pieces that make this thing tick? It turns out there are really just three essential parts that make all the magic happen.
So the first thing you'll find, of course, is the power source, the electric cell. Now, you and I would just call this a battery, right? It's basically a little self-contained packet of electrical energy you can carry around. And what's absolutely crucial about any cell are its two connection points. You've got the positive terminal, that's the little metal cap that sticks out, and you've got the negative terminal on the flat end. And trust me, this whole positive/negative thing, it's going to be super important in just a minute.
Next up, we've got the part that actually does the work, the electric lamp. Its entire job is to take that energy from the cell and turn it into something useful, in this case, light.
Now, what's really interesting is the technology here. Older flashlights use what's called an incandescent lamp. It has a tiny wire, a filament, that literally gets white hot and glows. But most modern flashlights use LEDs. You can think of an LED as a one-way street for electricity. It only lets the current flow in a single direction. That little design difference makes them way more efficient, which is why they've pretty much taken over.
So, we have a power source, the cell, and we have something to power, the lamp. But just having them rattling around in the same box isn't enough. How do we actually connect them to make light?
This is really the heart of it, right? It's not enough to just have the parts. They have to be connected in a very specific way for anything to happen at all. This is the big aha moment when it comes to understanding electricity. And the answer is we need to create something called an electrical circuit. Probably the best way to picture this is like a racetrack. The electricity has to have a complete, unbroken path to leave the starting line, the power source, go through the lamp, and make it all the way back to the start.
So here's the #1 rule you have to remember. Electric current flows in a complete loop. It has to go out of the positive terminal, travel through the lamp, and come back into the negative terminal. The lamp will only glow if that path, that circuit, is totally unbroken.
But a circuit that's always on isn't very useful, is it? We need some way to control that flow of electricity. And that brings us to the final piece of the puzzle inside our flashlight, the switch.
The switch has one simple, elegant job: to be our control. If we stick with our racetrack analogy, the switch is like a drawbridge.
When you slide that switch to the on position, the drawbridge comes down, closing the gap in the track. The circuit is complete, the current flows, and boom, the lamp glows. But when you slide it to off, the drawbridge lifts up. That creates a gap in the track, and the flow of current just stops, instantly.
Okay, so we've got our power, our lamp, and our switch. But what about the racetrack itself? I mean, why are the wires inside the flashlight made of metal, but the case is made of plastic? Well, the answer comes down to two very different kinds of materials.
Have you ever stopped to wonder about this? You see it everywhere, right? On your phone charger, on big power lines. It's not a random design choice. There's a very, very good reason for it.
There's a really clever and simple way to figure this out. You can build what's called a conduction tester. It's really just an open circuit with two free wires at the end. If you touch an object with both wires and it completes the circuit, the lamp will blow.
And when you start testing different things, a really clear pattern shows up. Touch the wires to a metal key and the lamp lights right up. But if you touch them to a block of wood, nothing. This shows us that some materials let electricity zip right through them, while others just block it completely.
And this leads us to two super important categories. We have conductors, like the metal in a wire, which let current flow easily, and then we have insulators, like plastic or rubber, which stop the current in its tracks. To build any safe and useful circuit, you absolutely need both. And this is where it gets really, really important. Insulators are there to protect us because, and you should never forget this, our own bodies are also conductors of electricity. That plastic coating on a wire is what stops the electricity from taking a dangerous shortcut through us.
And it all comes back to this one simple, powerful idea of the switch. Every single electrical device, from this little flashlight all the way up to a supercomputer, is fundamentally about controlling a circuit, opening and closing a path for electricity to flow.
So there you have it. By taking apart something as simple as a flashlight, we've uncovered the 3 golden rules that power our entire world. You need a power source, you need a complete circuit, and you need a switch to control it. So the real question isn't just what other devices you can now explain, but think about how this simple circuit, when repeated billions of times on tiny silicon chips, is what makes it possible for us to even have this conversation right now.